Today, we're going off on an extension of that exercise we've done where, remember when I was drawing a whole bunch of dots and I asked you to just notice how they're all made up of triangles, right? So, just to keep it simple, let's take that as my triangle, and I cut it up. Given information about one triangle, you would have to use information from that to move on to the next triangle, which will be used to move on to the next triangle. Right? In essence, you could think of it as you starting at one location and you're traveling along the shape. So now these triangles that I've drawn on the board, they're not conventional shapes, obviously. They just still look like triangles to you. But we're practicing the ability to navigate, to move from one triangle to the other. Because if you can do that, we can move from one shape to another. Get what I'm saying? So let's start with the easy stuff and extend it to the harder material. My question to you is this. Take a look at each of these pieces. What section, what side, what angle, what piece of this shape is shared by both triangles? So just, well, I don't even know what angle we're starting with, right? So adjacent, opposite, hypotenuse are not words I'm looking for. Just describe the location of this gigantic shape that is shared by both triangles. Yeah, go ahead.
The first one?
Yeah.
The altitude.
Yeah, the altitude, or the middle. I really appreciate the fact that you are using the proper terminology. The altitude is shared by both triangles. In other words, let's pretend I have enough information to do SOHCAHTOA, which means I can figure out all the parts of this triangle, right? But that's not my goal. What if I wanted to figure out that angle? Well, the information you have on this triangle can be transferred over. Maybe we can share the information to find the altitude, which can be used to find the angle. You get what I'm saying? SOHCAHTOA will open up your world from just sides or just angles to navigating anywhere we want. That relationship is super important, okay? And I keep on mentioning how it's sort of full of wonder, and Tom doesn't agree with me, but it's pretty awesome stuff. It is, it really is. Okay, just the idea of using how we explored a circle to get to where we are. How about this one? Not necessarily size. What section appears to be shared? What is a common area of this gigantic picture here? Yeah? The hypotenuse, sure. Well, it's one line. However, I actually don't know what these two lengths are. I don't know if they're equal or not. What's another portion that you know for sure is the same or are shared by both? The intersection. What about the intersection? Yes, well, the intersection is shared. What about it? Give me a specific number. What's so special about it?
It intersects at an opposite angle.
Opposite, the same angle, opposite. So, according to opposite angle theorem, I guess we can call it OAT. We don't define angle here. According to opposite angle theorem, those two angles are the same. So if I could figure out all the information, let's say from here, we use SOHCAHTOA to figure out all the information here, and we know what that angle is. If that's the case, we know automatically what that angle is. And then we can solve the others. See how we're moving from one location to another? That's the essence of these multiple triangle questions. You had a question? No? Okay. Another thing, if you really wanted to, or if I wanted to extend that to you, I could have just simply told you, hey, that line and that line are parallel. How does that make your life easier? Go ahead.
Means that theta has the same angle as the angle down.
Perfect. Do you know what that's called? Mathematically?
Z.
Yeah. So parallel line theorem in the shape of Z, or you can call them alternate angle theorem, alternate angles. Okay? They're part of the same Z pattern. Yeah. So it doesn't have to be size. It could be angles that help us travel between one location to another. Very quick. What area is shared by both triangles? And I hope you can see both of this. The hypotenuse of this is the what of the other?
The altitude.
Yeah, I guess, right? Well, it depends on how you, this is spatial. This depends on how you rotate your shape. If you take that and rotate it, yeah, that would absolutely be the altitude. What if you took that shape and decided, you know what, I like it sort of flatter? Base. Exactly. But you're talking about the same location, so be careful how you communicate, it's very important. So it's that location. If I have this piece, I could transfer over from one triangle to another. Same thing. And this is special because you'll see it today in one of our examples. See it? The base of one is the, I don't even know what we call that, the top. The base of the other, right? And if I draw a square in one, in other words, 90 degrees in one, you can automatically assume it is 90 degrees on the other side because of, can you remember that theorem?
The F.
Well, it's not really an F, it's basically knowing that if one side is 90 degrees, the other side must add up to a 180. It's up to an S. Supplementary angles, right? Oh, I didn't hear. Sorry, Nana. Maybe the recording picked it up. All right, how about this one? It gets a little harder, it gets a little bit trickier. Unless you see it. What side is shared?
The base or the F.
Sort of, not all of the base. Someone else? Because the base of this triangle is not exactly the same.
Hypotenuse.
Hypotenuse? Well, you know what? How about I draw this out? That's one triangle, and that is the other triangle.
It's not right.
The hypotenuses are actually different. What is the same? Oh, people. Ready? This part. This and that are the same.
I thought the triangle was like.
Well, yes, you could say that that's a triangle. We haven't yet worked with non-right angles yet. So hold that thought. When we get there, I'm going to come back to you, okay? And you can answer my questions for me, yeah?
Isn't the right bisector shared?
Right bisector. Oh, so this one, yes, it's true. However, if I were to draw this as that triangle, we don't have the techniques, we don't have the tools to work with non-right angles yet. So this makes it a little different. So up to this point, we can say these two heights or these two altitudes are the same. Okay? Another thing that might help you later on is this length and that length. They're part of the same line, so there is a kind of relationship. Here's one example, and you'll see this in the harder questions. If I said this was, let's keep it simple, 10, right? And I didn't know this, but let's call this x. By default, what is that length? That shorter length? Yep.
10 minus
10 cut away x, exactly. Right? It used to be 10. This is the x portion, so how much is left? Well, subtract x, that's how much is left. Get what I'm saying? So there are ways to connect other sides as well, beyond just making things equal. And you'll see this happen in some of the more challenging questions. Last one before we move on today. 3D. Does everyone see how this could be 3D? Some people don't, but it seems most of you are nodding your heads. This is obviously not 90 degrees if I were to draw it in a 2D world. Now that looks more like 90 degrees. But art class, you have to use perspective. And this is where sort of geometry and art sort of come together with the math. Because again, I keep trying to vouch for the fact that math is a form of art. You might not believe me. Anyways, if I took this, if this was a piece of paper and I bent it towards you, I think you can imagine that the 90-degree angle doesn't look like 90-degree angles. But because of that square, you have to assume it is. Right? Who here is not quite seeing it just yet? I mean, I could twist it up a little bit. Just a little bit? Okay.
Mr. Kim, what would the shape look like? How would the 3D shape look like with all of the sides connected?
Oh, I don't see that.
Do you see 3D now? So this is a cliff. There are people hanging out looking at the river below. Do you see it? So this is what I mean, like, as long as you see the perspective, if you can see it without this picture, amazing. If you needed that picture, that's fine. But continue to sort of push yourself to try to see a 3D shape inside a piece of paper. Okay? So these things will pop up. This is what I mean by the 3D and getting to know your 90-degree angles. What if I had something like this? Okay? Q. Do you see it? Inside a cube, I could still create a 90-degree triangle inside, but it may not be right away. But just keep chewing on it. The idea that 90-degree triangles do exist, and in that case, this 90-degree triangle, let's try to make it solid now, okay, is connected to the base. And that base is also 90 degrees. See how it can get you can start adding layers of complexity to it? Okay? It's not even that much complex, but it just gets you to challenge your way of perception and your thinking. And this might pop up when we're doing SOHCAHTOA. If you can do SOHCAHTOA, we can start doing 3D shapes.